Okay, thank you very much. Today I'd like to talk about minimalism in modified gravity based on my collaborations with these people. Okay, first introduction. So why modified gravity? Okay, I think there are many motivations, but particularly I think these three are very important, I think. So first, mysteries in the universe, such as dark energy, dark matter, inflation, Big Bang singularity, maybe cosmic magnetic field also. And if we can replace some of them by modification gravity, that would be great. Okay, this is the first motivation. And the second, it would be great if we can help constructing a theory of quantum gravity. Okay, so superstring theory or Hodge-Institut gravity are those, such examples. And also, modified gravity may help understanding GR itself. Okay. After all, I think one of the best ways to understand something maybe just to break it and then reconstruct it. Okay. So also I think modification gravity can help testing GR. Okay. So in this sense, so modification gravity may be good for understanding GR itself. Okay. So these are three motivations. You may have more motivations, but at least three. Okay. And from the third motivation point of view, so I think it's important to understand GR itself. Okay. So let me remind you how we can count the number of degrees of freedom in general relativity. I think I did this in my lectures, but so just in case, I'd like to remind you. Okay. So we start from 10 metric components. So we have metric in GR. So the symmetric and non-degenerate 4x4 matrix. So we have 10 components. And we want to go to the phase space. So we multiply 10 by 2. So we have a 20-dimensional phase space at each point. Okay. And then in order to go to the phase space, Hamiltonian formalism, it's convenient to decompose 4-dimensional space-time into 3+1, the so-called ADM decomposition. Okay. So let me explain a bit about this. So we have lapse n and shift ni. Lapse is here and shift is here, and the 3D metric Hij here. Okay. So these are the 1 and the 3 and the 6. So we have in total 10 components. Okay. By plugging this into the Einstein reduction, which is action for GR, general relativity, then we get this expression. Okay. Here, Kij is so-called Dixon's curvature, measuring how constant time surface is embedded into the space-time. And so this includes the time derivative of 3D metric. The 3D metric is here, okay, but doesn't include the time derivative of lapse or shift. Okay, this is a spatial derivative. And also this part is a 3D curvature, so that includes the spatial derivative of this guy, but doesn't include the time derivative. So the action doesn't include the time derivative of lapse and shift. Okay, so we are in the Hamiltonian formalism, so that we need to compute the momenta conjugate to all variables, and so we have pi n equals 0, pi I equals 0, where this is momenta conjugate to n, and this is momenta conjugate to ni. Okay, so they are 0, meaning that we have a kind of algebraic equation in the phase space. Okay. So they are called constraints, and actually they satisfy some conditions. So then they are called first class. Okay, let me explain what they are. So okay, so in the end, I think what I want you to remember is that the first class is better than second class, as always. Okay. And so second class constraint reduces one phase space dimension. Okay, and on the other hand, first class constraint, one first class constraint can remove two phase space dimensions. So in this sense, first class is better than second class. Okay. And also the first class constraint can actually generate a symmetry. And so in this sense, this first class constraint is special. Okay. And also, as you know, 2 is 1 plus 1. So the one first class constraint is equivalent to pair of second class constraints. Okay. So even in this case, first class is better. Okay. And as I say, so this pi n and pi I first class constraints, because when we compute the constraints, a Poisson bracket, between this guy and other constraints, then they vanish. And also same for pi I. And in this case, they are first class, okay, as you can see from here. And so they are first class, and each of them remove a two phase space dimension at each point, okay. And also GR has more first class constraints because, as I said here, the first class constraint is related to symmetry, and general relativity has diffeomorphism invariance. So we can change coordinates, four-dimensional coordinates to any coordinates, so that this is symmetry. So we have 4 generators of 4D diffeom. They are first class constraints. So we have 4 plus 4 first class constraints, in total 8. Okay. So we started with a 20-dimensional phase space and 8 first class constraints, and each of them remove 2. So we end up with a 4-dimensional physical phase space. Okay. This corresponds to 2 local physical degree freedom. Okay. When we go from 10-metric components to phase space, we multiply by 2. So from the physical phase space, we need to divide this 4 by 2, then we get 2. Okay. So the GR has a 2-degree freedom at the fully nonlinear level. Okay. So when we modify GR, the minimal number of degree freedom in modified gravity should be 2, because we know that from observation in our universe, we have gravitational waves, okay, which has a plus mode and cross modes. And indeed, this 2-degree freedom of GR, those are gravitational waves. Okay, so we cannot reduce from 2 to something 1 or 0. So we need to have at least 2. Okay, so the question now is this one. So can this minimal number be saturated? So this is a question that I would like to ask in this talk. Okay, and the theories that saturate this number is called minimally modified gravity. Okay, so this is the subject of the next section. And so I want to ask this question related to this question. Okay, so if the answer to this question is no or yes, okay, so suppose this answer to this question is yes, then the answer to this question is no. Okay, GR is not unique. Okay, we can modify GR without introducing extra degree freedom. Okay, and however, a common knowledge such as Lovelock theorem or effective field theory tend to say yes. Okay, so we need to do something. Okay, let me explain what they say. Okay, so the Lovelock theorem says yes if we assume say yes to this question and no to the previous question. Okay, and so answer to this question is yes if we assume 4 dimensions and different invariance and metric only, and up to second order equation motion of this form. Okay, and also the effective field theory, namely the derivative expansion, tend to say yes to this question and no to the previous question. At least at low energy, if we assume 4 dimensions and different invariance and metric only. Okay, and so if we assume say these 3, and of course we want to construct the action, which is integral of some scalar multiplied by volume, okay, 4-dimensional volume. And scalar can be made of some metric and its derivatives. Without derivative, scalar is just a constant, which corresponds to cosmological constant. With one derivative, no term, Christopher symbol is not the tensor, and so we cannot construct a scalar with just one derivative. So with 2 derivatives, we can use rich scalar, okay, and then leads to Einstein reduction. Then if we truncate at that point by this derivative expansion, then we end up with GR, general relativity. Okay, so in this sense, at low energy, effective field theory says yes to this question. Okay, however, wait a moment. So the cosmological background breaks 4D diffeom while keeping 3D diffeom. Therefore, maybe this assumption, 4D diffeom invariance, may be too strong. Okay, maybe we can relax this to 3D diffeom. Okay, but if we try to find a theory, metric theory, namely a theory with only metric, no, metric theory means that okay, theory includes metric, but anyway, so if we consider metric theory, say only metric with 3D diffeom, but with the broken 4D diffeo, then typically we end up with 3 local degree freedom, not 2. Okay. For example, scalar tensor theories, or EFT of inflation, EFT of dark energy, or Hodge-Alpha gravity. Okay, let me explain this a bit about this. Okay, so this is an example, simple example of scalar tensor theory. Okay, so this is the covariant action of a simple scalar tensor theory. Here, this is a Ricci scalar multiplied by some function of scalar field phi. Okay, and this is a function of x, which is a usual kinetic term, and scalar field phi. Okay, and so then let's consider the ADM decomposition, 3+1 decomposition that I already introduced. Lapse and shift and 3D metric. Plug this to here, and also let's choose the gauge so that scalar field phi is time. This is good as far as the derivative phi is time-like. So let's assume that the derivative phi is time-like, like cosmology, or inflation, or dark energy, or something like that. Then the derivative phi is usually time-like. Then we can choose this in general. In this case, x defined in this way is written in this way because the metric is given by this, and inverse of the metric, G mu nu upstairs, is given by this. 0, component is just this, minus 1 over n squared. And then the 0, component here, and because phi is t, we have just here Kronecker delta, mu 0. So we have this one. Okay. And so plugging this and this to here and here and here, and the metric to here, we get this kind of action. Okay. In a sense, scalar fields disappear by choosing this gauge. So everything is written in terms of the metric. Okay. Of course, a 3+1 decomposition, but everything is written in terms of the metric. Okay. And but we know that this theory has not a 2, but a 3 degree of freedom, because this is equivalent to this action, which has a scalar. Okay, not only metric but also scalar, and we usually have 3 degree of freedom. Okay, so metric theory with 3D diffeo, but with broken 4D diffeo, tend to have 3 local physical degree freedom. This is not what we want. Okay, the real question here is this one: is GR unique when we assume these 4 assumptions? Okay, 4 dimensions and 3D diffeo invariance and the metric only, and 2 local physical degree freedom, which corresponds to 2 polarization of transverse traces gravitational waves. Okay, this is the question that I want to ask. Okay, and the answer is actually no. And the theories that satisfy these 4 conditions are called minimally modified gravity, MMG. So this is the subject of this talk. Okay, I hope this is clear enough. If not, please ask question at any time. Okay, and I'd like to explain here examples of type 1 and type 2 minimally modified gravity, MMG. Okay, but before that, I think I need to explain what type 1 is and what type 2 is. Okay, this classification is very simple and very universal. Okay, let me explain this by using the simple scalar tensor theory. Not yet MMG, but simple scalar tensor theory. Okay, so this is the action of simple scalar tensor theory in the so-called Jordan frame or matter frame. Okay, so this is a 4D. 4D Ricci scalar is multiplied by some function of scalar field, and we have some kinetic term and the potential, if you want, for scalar field here. But the important point is that matter action is written in terms of matter fields and this metric. Okay, so the scalar field doesn't enter here if we use this metric. Okay, so this is the reason why this so-called Jordan frame is often called matter frame. Okay, so the matter action is simple. Okay, and so this looks like modified gravity because Einstein heavy action is multiplied by some function of scalar field. Okay, indeed this is modified gravity. Okay, and but the interesting thing is that we can perform the so-called conformal transformation to define new metric, so that by multiplying the metric by some function of scalar field, which is the same form as this function, we can define new metric, the so-called Einstein frame metric. Then plugging this, solving this with respect to this metric, then plugging here, we get this. Okay. In this case, this function is removed. So we have just the Einstein reduction. Looks like a GR. So do we call this GR? Actually, no. Because in this case, the matter action is a bit complicated. Okay. So the previously, matter action was written in terms of the metric only. But here, because of the new definition of the metric, the matter couples to this combination of metric and the scalar field. Okay. So when matter is excited, then both metric and the scalar field are excited, and they propagate according to this action. Then we measure this combination by matter at different points. Okay. In this way, gravity is modified. Okay. So gravity is modified because of non-trivial matter coupling. Let's call this type of modified gravity type 1. Okay. On the other hand, there are more general scalar tensor theories where there is no Einstein frame. Let's call them type 2. Very simple. Let me repeat. Type 1, there exists an Einstein frame. Therefore, this kind of theory can be recast as GR plus extra degree of freedom plus matter, which couples non-trivially by change of variables. Okay, this is type 1, very simple. And whatever is not type 1 is called type 2. Okay, so type 2 doesn't have Einstein frame, and therefore cannot be recast as GR plus extra degree of freedom plus matter by any change of variables. Okay, this is type 2, very simple. And any modified gravity should fall into either type 1 or type 2. Okay, this is a very simple classification and very universal classification. Okay, and when we apply this classification to minimally modified gravity theory with 2 degree freedom, we call them type 1 MMG, type 2 MMG. I'd like to show some examples. Okay, so let me think about type 1 minimally modified gravity. So by definition, number of degree freedom is 2, and by definition, type 1, there exists an Einstein frame. Therefore, we can recast this theory in the absence of matter. This can be recast as a general relativity. Okay, but the matter coupling is non-trivial. Therefore, we can this theory can be recast as GR plus matter, which couples non-trivially by change of variables. In other words, we can start from GR, then perform some change of variables to generate any type 1 minimally modified gravity. Okay, this is a completely systematic construction. Okay, all type 1 minimally modified gravity can be reconstructed in this way. Okay, so as we know, at least as far as know, the most general change of variables is canonical transformation. So we can start from GR, then perform canonical transformation. That's it. Okay. However, there is some non-trivial thing. There is something subtle. So that if we couple matter just after canonical transformation, then something wrong happens. Indeed, just after canonical transformation, we have diffeo. Diffeo is not broken. After canonical transformation, diffeo looks a bit non-trivial, but it's there because it is GR written in a different code, different variables. Okay, but if we couple matter in a minimal way, then the matter has some diffeo invariance by itself, usual diffeo. On the other hand, gravity part has a diffeo which is non-trivially written. So by combining them, put them together, they are not consistent. Therefore, by adding matter, it breaks diffeo. Then the symmetry is broken, meaning that first class constraint is downgraded to second class. As I said, first class removes the 2 degree freedom, but second class removes only 1. So this means that we have extra degree freedom in phase space. Okay, 5 minutes. Thank you. And then this is inconsistent. We need to do something. The answer is very simple. We can gauge fix before adding matter. By doing that, first class constraint is split into pair of second class constraints, and this is as good as first class constraint. One first class constraint is equivalent to pair of second class constraint. Okay. Then by adding matter, we have a consistent theory. Okay. So in this way, we can construct any type 1 minimally modified gravity. Okay. And this is one example. Okay. So the so-called f of h theory with this kind of choice. And indeed, this can fit the Planck data better than lambda CDM. Okay. So the type 1 MMG is useful, I think. And this is very simple. And let me go to the type 2 because I don't have enough time. So the type 2 minimally modified gravity has again a 2-degree freedom, and there is no Einstein frame because of the definition of type 2. Therefore, this cannot be recast as GR plus matter by change of variables, any change of variables. Okay. Is there such a theory? Indeed, yes. And one example is minimal theory of massive gravity. And I think I explained this a bit about this in my lecture. So let me consider another example, which I proposed with Antonio. Okay. So this is what we call later we call the VCDM because of the reason I will explain now. Okay. So this can be constructed in a simple way. So we start from the Hamiltonian GR with 3+1 decomposition. Then we perform canonical transformation as in type 1. We have a new frame. And instead of adding matter, we just add a cosmological constant in a new frame. And then gauge fix. And if you want, we can add matter in this frame. Then we end up with type 1. But we don't. Instead, we go back to the original frame by inverse canonical transformation. Then perform the Lagrangian transformation to go back to Lagrangian, then add matter. Okay, we go back to the original frame, then matter. Okay, we travel to somewhere else, we pick up cosmological constant, come back, then we add matter. Okay, this is the construction. Then actually like this, and so indeed we have recently shown that there is no Einstein frame, and indeed actually this is equivalent to so-called Cascouton. Okay, and also from the Friedman background, any Friedman background can be reconstructed by choosing proper function V of phi. Okay. Then the speed of gravitational wave is 1. There is no extra degree of freedom, so this is very safe. And because we can construct any Friedman background, this can reduce H-naught tension. Okay. So this is the proof of the absence of Einstein frame, namely this theory is type 2. But for this purpose, it was very useful to define the classification. So we have type 1 and type 2, depending on whether we have Einstein frame or not. Okay. Also, we classify into type 1A, and so type 1 into type 1A and type 1B, and type 2 into type 2A and type 2B, depending on whether speed of gravitational wave is 1 or not. Okay. And type 1A have a conformal type canonical transformation from GR, type 2 not. And so we have some populations. Because of this proof, we have now example of type 2A, type 2A, meaning that there is no Einstein frame and speed of gravitational wave is 1. Okay. So proof is very easy, but probably I don't have time. But maybe I can skip. I can sketch. So we analyze the gravitational waves in this theory. Then we show that speed of gravitational is 1. So this is type 1A or type 2A, either this one or this one. Then we consider the most general type 1A MMG and studied Bianchi 1 universe for Cascouton or VCDM and type 1A MMG. Then they are different. So this means that this theory is not type 1A. Combining 1 and 3, we end up with the conclusion that this theory is type 2A, meaning that there is no Einstein frame. Simple, very simple. So that we have now population here. Very happy. And also this theory can be extended to realize weaker gravity at late time. So instead of adding cosmological constant in the other frame, we pick up not only cosmological constant, but also dark matter, any dark matter model. Okay, then come back, then add a standard model. Okay, so we need to stop soon. And do we have a time for questions? Maybe I'll try to finish soon. Anyway, okay. So from here, we can reconstruct the h of z background and also the strength of gravity as a function of z for dark matter. On the other hand, speed of gravitational waves and strength of gravity for standard model is the same as GR. So they are safe, but we can modify gravity for also the not only for the background, but also for the perturbation. So may reduce H naught tension and SH tension at the same time. Okay, so maybe I should skip this, but I just want to say that for the Einstein gas bound gravity, we can construct a consistent theory, but in the framework of minimally modified gravity, and this is type 2, actually type 2b. Okay. Okay. So let me go to the and also we have constraints from what I think, including the propagation gravitational waves. Okay. Let me summarize. And so minimalism in modified gravity. So minimal number of degree freedom in modified gravity should be 2, and this can be saturated. And theories, those theories that saturate this number is called minimally modified gravity. And type 1 MLG has one Einstein frame. Type 2 doesn't. And this provides a universal classification of any type of MLG. And also this can be applied to any modified gravity. And then I showed some example of type 1 MLG. So this can be constructed by starting from GR, perform canonical transformation, gauge fix, then adding matter. That's all. Still, there are rich phenomenology such as effective equation of state of dark energy without extra degree freedom, and G effective, and so on. And this theory, f of h, can fit Planck data better than lambda CD. And example type 2 MLG, minimal theory massive gravity, and also the VCDM and Cascodon. We have proved that this is indeed type 2. There is no Einstein frame. Okay. And this may reduce H naught tension. And we also extended this theory from VCDM to VCCDM because CDM is coupled to conformally transformed frame. So, and then lambda CDM, lambda is replaced by V. Okay. And this may reduce, this may address both H naught tension and SH tension. So stay tuned. Okay. And I skip this. Anyway, this is our MLG theory, which corresponds to D equal 4 Einstein gas bound gravity, is a unique theory. Okay.
Yeah.
Thank you very much.
Thank you very much, Shinji. We have already a question. Henri?
Yes, good morning. Thank you for the talk. I wanted to know, you showed a few a procedure for obtaining these type 2 models. I wanted to know which type of symmetry this type 2 brings such that there is no Einstein frame for its description.
Yes, so here, yes, so we break time difference. Yes, so by going to the first we go to the Hamiltonian. So already apparently we have so because 3+1 decomposition, we don't respect the 4D difference. But of course, at this level, theory is not changed, so that we have 4D difference. And but we perform canonical transformation to go to a new frame. Still, we have 4D difference, which is non-trivially hidden. Then we add cosmology constant. By adding cosmology constant in the other frame, we already, at this point, we break 4D difference, time difference. But we still keep 3D difference.
Okay, but this type of models are extremely constrained. I mean, in particle physics, in many contexts, they are extremely constrained, no?
Yes and no. Indeed, actually, no. If we minimally couple matter here, yes. So we assume that matter action has a 4D difference. at least approximately. Then we add matter here. So the 4D field is preserved in the matter sector, and the Lorentz symmetry in the matter sector is broken only through gravitational loops, which is very weak. So it's okay.
Okay, thank you.
You're welcome. And also it's important to keep the parity here. I mean, we keep parity, I mean, in time and space. So in gravity sector. So yes, I mean, otherwise I think the gamma ray burst, I mean, I think polarization of gamma ray burst constrained very strongly the, I think, CPT violation in the matter sector.
Yes, gamma ray burst constraint, especially the modified dispersion equation that you showed.
Yeah.
Yes.
Okay.
So here,
I think,
yeah, yes. So yes.
Yeah, if it's quick.
Dispersion relation is.
Okay.
Okay, thank you.
Thanks a lot, Shinji, for your talk. We need to move on.